Midas NFX Lecture 10, Joule heating problems. Joule heating means when you pass a current or impose a electric potential through a conductor, there will be a heating effect through I square R heating. So this is Joule heating problem. And now we open a case, give it a name, and import the geometry. And this is the first step. The second step, the material. And we can define the material using CFD module. So this problem is solved in CFD module. I choose tungsten material, and the electrical conductor will be the resistivity, and I look it up from the internet. The value is 5.65. So I enter 5.65 e to the minus 8, and alpha equals 4.5 e to the minus 3. So these are the properties of the tungsten that I look up from the internet, and the reference temperature will be 20 degrees. So these are the properties for electrical conductor for tungsten. So I have added tungsten to the material list, and I'll connect the material with the geometry. Make sure that you use CFD module and the geometry is connected to tungsten. So this is the end of second step. Step 3 will be meshing. I'll choose this geometry and accept the default mesh size and mesh. So this is the end of step 3. Step 4, CFD analysis. First of all, I'll give it a ground potential, so 0 volt. So I'll ground at the top surface, and I'll give it a current, electrical current, at the bottom surface of 1 milliamp. And this is the current, 1 milliamp ampere. And then we'll set the convection condition. All the surfaces that are in contact with the air should be selected. So the top surface and the bottom surface are deselected because they are in contact with the electrodes. The ambient temperature will be 20 degrees, and the coefficient of convection is 10. This 10 watt per meter square K is the coefficient of convection for stagnant air, the air with a velocity of 0, stagnant air. For forced convection conditions, for example, you direct a fan, a very strong fan, on the surface, this may be as high as 33. So for stagnant air, the air with velocity of 0, the convection coefficient is 10 watt per meter square K. So this is the convection condition, and we impose the convection condition so that the heat will dissipate it from these surfaces. So I have finished with the step 4. For step 5, analysis, I'll choose steady state. If you choose transient and steady state, there are differences in that in steady state the time is infinity and the system reaches equilibrium. For example, thermal equilibrium, all the temperatures are fixed. So if you are running for transient thermal analysis or transient CFD analysis, there are two things that are different from steady state condition. The first thing is the initial condition, for example, initial temperature, initial pressure, velocity, etc. And the second thing would be the time to calculate. For example, you are calculating an hour or 2 hours of time. So these are the difference. So for steady state condition, we don't need initial conditions or calculation time. So for the analysis control, we'll select solid heating. and also there is electrical field. And as a custom, usually I'll give it the initial temperature, and it is a good habit to do that because in steady state condition the initial temperature is not very important because the time goes to infinity. So whether the initial temperature will be 0 or 20 degrees C, there's no difference, but it's a good habit to change the initial temperature. And also the thermoelectric effect should be checked because this is the most important effect for this problem, Joule heating problem. So for the analysis control, I did 4 things. The first one is check the solid heat transfer. The second is check electrical field. And the third is not necessary, but I did change the initial temperature of the solid. And then beware that the gravity is along the z-axis and downwards. So z-axis is upward and downward is the earth. And then I check the thermoelectric effect. So we have finished with the analysis control setting. So I can go ahead and calculate. And it takes a little bit of time for calculation, so I'll stop recording. The iteration is still running, but the temperature, the blue color line, is more or less stabilized. So I'll load the result file. And this feature is one of the most favorite feature in Midas for me. I like this feature because even if the solution is not finished, you can look at the result. So you can see that the potential, electric potential, is increasing from 0 to a certain voltage. And this is the current. You can see that the current is proportional to the resistivity because it is heating by I square R. And resistance equals resistivity times L over A. Resistivity is a material constant and length of the bar is constant. Therefore, the larger the area, the smaller the resistance. So you can see that here the larger area gives you the lower resistance and this is higher resistance, so they are different. And we can see the temperature difference. We have temperatures. We can probe for the temperatures is about 102.5 degrees C, and the top temperature and the bottom should be the same, but it is different. You can see that the color is different, but the numerical value is very close, right? A difference of about 2 digits or 3 digits on the decimal. And this effect is a result of gravitation because the hot end at the top and the cool end at the bottom is a result of gravitation. But the gravitation effect is very small. You can see from the numerical values here. And the solution has finished, so I can load the final result. And this is the lecture 10, Joule heating effect, where a conductor was imposed upon by a current or potential, voltage, electrical potential, and through I square R heating, the system temperature increases. So we can see that there's a temperature difference. So the temperature goes from 20 degrees to 102 degrees by a heating of 0.001 ampere current. So this is lecture 10, Joule heating problem.